Hey PTE aspirants! Welcome back to our channel, your go-to place for mastering the PTE academic and PTE core. In today's video, we're diving into a fresh Retell lecture practice, just like you'll face in the real exam. I'll play the lecture first, and then you'll hear the perfect model response, so you can boost your fluency, content, and pronunciation scores. Make sure you grab a notebook for keywords, because this is your moment to practice like a pro. And hey, before we dive in, hit that subscribe button so you never miss a single practice session that could make all the difference in your PTE results. High-speed rail, often referred to as bullet trains, represents one of the greatest achievements in modern transportation engineering. Originating in Japan with the Shinkansen in the 1960s, these trains can travel at speeds exceeding 300 kilometers per hour. Countries like China, France, and Germany have also developed extensive high-speed rail networks, reshaping travel and reducing reliance on cars and airplanes. Engineering bullet trains involves designing lightweight yet strong carriages, aerodynamic shapes to reduce drag, and advanced track systems that minimize friction and vibration. Safety features, such as earthquake detection systems in Japan, ensure passenger security. High-speed rail is also environmentally friendly compared to air travel, producing fewer emissions per passenger. However, challenges include the enormous cost of building infrastructure and maintaining tracks. Despite these difficulties, high-speed rail continues to expand globally, symbolizing speed, efficiency, and sustainable transport for the future. The lecture was about high-speed rail, starting with Japan's Shinkansen and spreading to countries like China and France. Trains run over 300 kilometers per hour, using aerodynamic designs and advanced tracks. Safety systems and eco-friendliness were emphasized, though costs are high. Overall, bullet trains represent efficient and sustainable transport. Aerospace engineering focuses on the design and development of aircraft and spacecraft, combining principles of aerodynamics, materials science, and propulsion systems. It has two main branches: aeronautical engineering, which deals with airplanes and helicopters, and astronautical engineering, which involves rockets and satellites. Engineers in this field face challenges such as reducing weight while maintaining strength, developing efficient engines, and ensuring safety in extreme conditions. For example, spacecraft must withstand both the intense heat of launch and the freezing temperatures of space. Similarly, airplanes require advanced navigation systems and fuel efficiency to serve global travel demands. Aerospace engineering has driven remarkable achievements, from the Wright brothers' first flight to the Apollo moon missions and modern commercial aviation. It also plays a role in defense and telecommunications through satellites. Ultimately, aerospace engineering reflects human ambition to conquer the skies and beyond. The lecture explained aerospace engineering covering aeronautical and astronautical fields. It noted challenges like balancing weight, propulsion, and safety in extreme conditions. Examples included space missions, aircraft systems, and satellites. Aerospace engineering contributes to travel, defense, and communication, symbolizing humanity's ambition to explore the skies and space. The construction industry is increasingly adopting renewable building materials to promote sustainability. Traditional materials like concrete and steel, while strong, have large carbon footprints. Alternatives such as bamboo, recycled wood, hempcrete, and biodegradable plastics are now being used in modern projects. Bamboo, for instance, grows rapidly and has high tensile strength, making it suitable for scaffolding and even structural elements. Hempcrete, a mixture of hemp fibers and lime, provides excellent insulation while being eco-friendly. Engineers are also recycling materials, such as turning demolished concrete into aggregate for new construction. These renewable materials reduce environmental impact, conserve energy, and often lower costs in the long run. However, there are challenges, including durability, acceptance in building codes, and large-scale availability. Despite this, the trend is clear. Renewable materials represent the future of construction, combining innovation with environmental responsibility. The lecture was about renewable building materials such as bamboo, hempcrete, and recycled concrete. It explained their strength, insulation, and eco-friendly benefits, while also noting challenges like durability and regulations. Overall, renewable materials reduce carbon impact and represent the sustainable future of construction. Space exploration depends heavily on advanced engineering, from designing rockets to creating life support systems. Since the launch of Sputnik in 1957 and the Apollo moon landings, space missions have expanded to include satellites, Mars rovers, and the International Space Station. Engineering challenges include developing propulsion systems powerful enough to escape Earth's gravity, building spacecraft that can survive radiation and extreme temperatures, and ensuring astronaut safety with oxygen supply, food systems, and protective suits. Robotics also plays a role, as machines can explore environments too dangerous for humans. Space exploration has practical benefits. Satellites improve communication, weather forecasting, and navigation. Scientific missions uncover knowledge about planets, stars, and the universe. Although costs are high, international collaborations like the ISS show the global importance of space research. Ultimately, space engineering reflects human curiosity and the drive to explore beyond our planet. The lecture described space exploration, starting with Sputnik and Apollo, and expanding to satellites, rovers, and the ISS. It mentioned engineering challenges like propulsion, radiation, and astronaut safety, plus the role of robotics. Space missions provide communication and scientific benefits despite high costs, reflecting human curiosity. Artificial intelligence, or AI, is transforming civil engineering by enabling smarter and more efficient project management. AI systems can analyze massive datasets to predict material performance, detect structural weaknesses, and optimize construction schedules. For example, machine learning algorithms monitor sensors in bridges or tunnels to identify cracks before they become dangerous. AI-powered drones can map construction sites, while automated design tools create efficient blueprints. These technologies save time, reduce human error, and improve safety. AI also plays a role in sustainability, helping engineers select eco-friendly materials and minimize waste. However, the use of AI raises concerns, including data privacy, cost of implementation, and the need for skilled operators. Despite challenges, AI is becoming a vital tool in civil engineering, blending technology with human expertise to build safer, greener, and smarter cities. The lecture explained artificial intelligence in civil engineering, noting uses such as detecting cracks, mapping sites, and creating efficient designs. AI improves safety, reduces errors, and supports sustainability by choosing eco-friendly materials. Although costs and privacy issues exist, AI is becoming essential for smarter and greener construction. If you found this practice useful, don't forget to hit that like button. It really helps more learners find us. And for daily PTE tips, model answers, and prediction topics, subscribe and turn on the bell so you never miss a lesson. Comment below with your score goal, and I'll share a personalized study tip for you. Until next time, keep practicing and keep aiming higher. You've got this.